Welcome back. So we'll consider yet some examples here. I really want to have fun with this lesson by considering some edge cases. Or you see why I call them edge cases now. So you see that this method is extremely useful for some problems that look unnecessarily complex. Okay, so what example? We want to solve the following differential equations. We solve the following. So the first one says we have the squared y, the x squared to be equal to sine squared x. Yes, yes. So I like this problem. So let's have a look at this. If you paid attention to the last lesson of the last chapter, the last lesson of the last chapter. There's no better way to put that. You recall that I did give you an equation there to solve, where I said you add if you add the square y the x squared to be equal to 0. What do you think the solution would look like? So this is an opportunity for us to solve that equation now, because that will be the homogeneous part of this equation. So obviously, this is a second order, yes, second order linear. Yes, it is linear. It is not. We don't have any product of y or any of its derivatives. So it is with constant coefficients. Yes, the coefficient of the square y dx square is 1, and it is non-homogeneous. Yes, we can see sine squared x is right here. So how do we solve this kind of equation? Now you might be tempted to say that yes, this is the square y dx square, and indeed this is a kind of differential equation that can be reduced to a first order differential equation and then solved in stages. What I mean by that is we know the square y dx squared, for instance, is maybe we would have a look at that or those kind of equations in another chapter. But if you have this the squared y the x squared, I'm not solving this equation yet. So I just want to show you we're solving this equation using the method of undetermined coefficient. No doubt about that. I just want to show you that you could just solve this in another way by recognizing that this is the x, this is derivative of the y, the x. So if we use some expression to represent the y dx, and that means the derivative of the y dx is sine square x. So if we say let p be equal to the y dx, this means some dp dx is equal to sine square x, which makes this or which reduces the equation to the first order ordinary differential equation, which is separable, so we can solve this the way it is and get our solution. But it means we will have to integrate sine squared x. Of course, you should know how to integrate sine squared x. You can simplify this and integrate it, um, which is fine. Once you are done with that, it will give you your dy dx. Then you can integrate again and get what y is meant to be as a function of x. So this first one will like giving you one constant, and when you do the integration of the y dx, whatever you get a p, you know it's the y dx, so you can equate it to the y dx and integrate again to give you another constant. So it takes care of the two constant of integration we are meant to have for the solution. So you can go about it that way and solve the problem completely. Whatever you get from that is correct, provided you've done it properly. So, but that's not our business here, okay? So, what to solve this? We can see that as simple as this is, it is a non-homogeneous second order ordinary differential equation with constant coefficients. So we can apply the method of undetermined coefficients here because yes, this is sine squared x. So you might be wondering, or you might wonder, why do we have sine squared x here? Don't forget we said that f of x should be of the form or should contain the components sine ax cos ax and so on and so forth. So it doesn't matter how you see this. If you see this as the product of sine x and sine x, it's still correct. And you might also see that something that can be written in another form that contains, let's say, cos 2x and all of that. We'll talk about that shortly. It's still correct also. However you see it, it is something that we can apply the method of undetermined coefficients to. So that means If that is the case, then we can say that we're given in this case y prime prime to be equal to sine squared x. Okay, its homogeneous part, its homogeneous part is, so how do you get the homogeneous part? Just y prime prime equals 0. So we have to solve this equation now. So if y prime prime is 0, then what is the auxiliary equation to this? Whose auxiliary equation is, what is the auxiliary equation? M squared. That's just what we have here. There's nothing else. So m squared equals 0. If m squared is 0, that means m is equal to root of 0, which is 0. So we expect, this is a quadratic equation. We expect two solutions. So this is basically telling us, depending on how you look at this, you can see this as m minus 0 into m minus 0 equals 0, which means that this is m equals to 0 twice. Okay. So this is a case of repeated roots. So and repeated roots are 0, 0. So by that, our complementary function will be c1 exponential 0 x. Just follow that rule. Once you follow the rule, you are safe. Okay. Don't begin to think too far about what it's going to look like, because it doesn't look like what you are familiar with or what you're used to. Just follow the rule. Once you follow the rule, you're good to go. So this is c1 exponential. Please don't forget that when we have repeated roots, this is the way we do it. c2 exponential, the same roots, 0 x. So then you can tidy this up. This is c y complementary is equal to exponential 0. That is 1. So this is just c1 plus x here, that is going to be just c2x, because this is 1 as well. So this is our complementary solution. That means that if you add this, the square y the x squared equals 0, the general solution to that will just be this if you add this homogeneous equation. So you can think of it, if it was y prime prime prime, so you know that you're going to have that to be c1 plus c2x plus c3x squared, and that's all. That's the solution. And you can verify that when you differentiate this twice, it's going to give you 0. Okay, you can check that for yourself. These are constants, bear in mind. And now that's not our business really. We want to get the general solution to this equation, which is non-homogeneous. So we now consider the f of x part. So we now say that from f of x equal to sine squared x. So can we simplify this further? If we want to, let's think about whether we should simplify it further, or just leave it this way. If we want to leave it this way, we will deal with the derivative of this. If we get the derivative of sine squared x, for instance, it's going to give us something like, now think about what happens from here. If you get derivative of sine squared x, it is going to give you 2 sine x cos x. Then if you get derivative of that, it's going to give you, you're going to just have products of sine x and cos x, products of sine x and cos x at some point, or cos x and cos x at some point, and all of that. So you might leave it this way. If you leave it this way, you'll be safe actually. So what you just need to know here is that this is a product of sine x and sine x. So this is just sine x multiplying sine x. So you can leave it as it is. And if you do, that means the only component here will be sine x, and its UC set is sine x and cos x. And then that's the only component you have present. And when you consider the products, sine x, which is sine squared x, of course, the UC set will just be the product of sine x and sine x. That's the sine x times sine x. That will give you sine squared x. Sine x times cos x, that will give you sine x cos x. When you consider cos x times sine x, that will still give you sine x cos x. There's no need to repeat that. This is a set, so a set does not have repeated terms. So then cos x times cos x, that will give you cos squared x. So these are the this is the UC set for the entire term. So does it have anything that is linearly dependent on what we have here? No, so there's no problem with this. So that means that our y particular could just be sine squared x, a sine squared x plus, let's write that small neatly. So this is going to be a sine squared x plus b sine x cos x plus c cos squared x. So that is fine. This is absolutely correct. We'll work with it now and see what our results will look like once we're done. Then we'll take another approach to simplifying this and see and compare the results as well. I said we just want to play around with mathematics here, so we see all the twists and turns possible with this method. All right, so of course, for us to simplify these or for us to evaluate y particular, we need to get y particular prime. So we need to differentiate this. Derivative of a sine squared x. What does that give us? That is a sine. So that is going to be the differentiating with respect to the core. That will give us 2 sine x. So this is a 2a sine x. Then multiply by derivative of the core. That is cos x. Then come here, derivative of this. This is a product of two functions. So derivative of sine x is cos x. So this will give us b cos x multiplied by cos x, that's cos squared x. Then when we differentiate cos x, it will give us sine x minus sine x, so this will become minus b sine squared x. Then derivative of cos squared x, that will give us plus c into cos squared x, that is 2 cos x. So that will be minus 2 cos minus 2c cos x, then multiply by sine x. So that should be minus 2c. Minus because derivative of cos x is minus sine x. So then we proceed with respect to the core, that will be 2c cos x then sine x. Okay, so that's what the derivative is for this expression. We're good to go. Do we have any like terms to put together? No, this is cos squared x, this is sine squared x, this is cos x sine x. Okay, this is cos x sine x as well. So I think we can put those two together. This is sine x cos x sine x cos x. So we have here 2a plus, sorry, 2a minus 2c. So this is 2a minus 2c into cos x sine x. Then this is plus b cos squared x, then minus b sine squared x. So with that, we're good to go. You might be tempted to say, okay, cos squared x plus, no, don't worry about that. Just leave it like that. So this is going to be cos y prime, yp prime prime, because we need the second derivative as well. So we'll differentiate this again for cos x sine x. So this is going to be 2a minus 2c, just reproducing the coefficients. Derivative of cos x is sine x, so that will be minus sine x, so that's minus sine squared x. Then the coefficient again, that is 2a minus 2c. Then derivative of sine x is cos x, so this will be cos squared x. Then plus this derivative of cos squared x, so we see that this is meant to be minus 2b. So this time around cos x, so then multiply by sine x. Then for this one, this is going to be derivative of sine x is cos x, so this is going to be minus 2b, then sine x, then cos x. All right, so that is that about that. Can we simplify these or tidy it up even further? Yes, we have these two to be the same, so this is basically going to be minus into minus 2a, sorry, minus 2a minus 2c into sine squared x plus 2a minus 2c into cos squared x. Then we have minus 2. This is cos squared x, so we can say this is minus 2b plus 2b. So that's minus 4b anyways. Minus 4b. Yes. That's minus 4b. Minus 4b cos x sine x. So that is that about that. Let us leave it that. So let's come back here. So we're good to go. So if we are going to substitute this in the given differential equation, which is y prime prime equals sine squared x, what do we have? So we know that but the given equation is y prime prime equals sine squared x. So we're just going to do go through the same process. Let's look at the terms present here. They are cos x sin x, cos squared x, and sine squared x. So we're good to go. We just identify their coefficients directly. So I want to go with cos squared x first. So what are the coefficients of cos squared x in y prime prime? Cos squared x is 2a minus 2c. So I'm going to have here 2a minus 2c. Okay, then is equal to, that's all we have on this side. So there's nothing else to check. Sine squared x, there's no cos squared x here. So 2a minus 2c should be equal to 0, which means a should be equal to c, or a minus c should be equal to 0. A equals c. So let's keep that. We don't have enough details to solve that completely yet. Then we move to the next one. Sine squared x is present. So this is going to give us sine squared x. And what will that be? Sine squared x will be right here in the second derivative, because just y prime prime is what we have here. And its coefficient is minus 2a minus 2c minus of 2a minus 2c. It should be equal to, the coefficient of sine squared x is 1. So this means that 2a minus 2c is equal to 1. 2a minus 2c equals 1. Sorry, 2a minus 2c should be equal to minus 1. Right, so does this solve our problem? This says a is equal to c. So if a is equal to c and this is 2a minus 2c, this will be 2a minus 2a equals minus 1. That's 0 equals minus 1. So that cannot work. So is there any issue with what we have done? Let's check the differentiation again in case there's any problem with that. So this was 2a sine x cos x and 2a sine x cos x. Then this is 2a sine x cos x. Then differentiating this, that is b cos squared x. Okay, then minus b sine squared x. Then minus 2c cos x sine x. Okay, that's okay. Then cos x sine x, that's 2a minus 2c. All right, then b cos squared x minus b sine squared x. Then for this is going to be minus 2a minus 2c cos x sine x. So I'll differentiate this. We get sine x, so that's sine squared x. We'll differentiate this, we get cos x, that is cos squared x. Okay. Then when we differentiate this, we get derivative of cos 2 cos that's going to be 2 cos x, then multiply by derivative of cos x, that's minus sine x, so that's going to be 2b minus 2b cos x sine x. All right, that's correct. Then derivative of that will be 2 sine x cos x, then that's multiplied by this. Yes, that's okay. Then what do we have to be like terms? We have sine squared x right here, and then we have cos x, cos squared x right here to be 2a minus 2c. All right, and we have this to be minus 4b cos x sine x. Okay, so that's correct. Then we have y prime prime equals sine squared x. So this is when y prime prime, what is the coefficient of sine cos sine squared or cos squared x? That is 2a minus 2c, and that should be equal to coefficient of cos squared x here is 0, and this is going to give us a equal to c. And when we get for sine squared x, so that is minus of 2a minus 2c, that is equal to 1. So this is going to give us 2a minus 2c equals minus 1. and we substitute here a to be equal to c. This is 2c minus 2c equals minus 1. That's 0 equals minus 1. So that cannot work. Obviously, that cannot work. So this is interesting. I'll be honest with you, I didn't know that this wouldn't work. Okay, but so it doesn't work. It doesn't work. So you can play around with it to see that it doesn't work because this is not going to work. So why is that so? The reason for that is because actually this sine squared x, it doesn't work obviously. So I didn't know it was not going to work. Believe me, I don't know. I didn't know it wasn't going to work. But obviously the reason for that, don't forget, we said that we talked about linear dependence the other time. We said that we could have, if you have something like sine squared x, you know that sine squared x can be written as 1 minus cos squared x. So you could bear that in mind while working here. And if you have that in mind, that means that when taking the coefficient of cos squared x, it cannot just be 2a minus 2c because this itself already carries cos squared x. Inherently, this carries cos squared x. So if I am just taking this to be the coefficient, the only coefficient of cos squared x here, then I'll be running into error. And the same thing applies to sine squared x. I know that cos squared x also can be regarded as 1 minus sine squared x. So if I am taking this as the only coefficient here of sine squared x, I am inherently committing some error, okay, or committing some mathematical fallacy, so to speak. So because of that, when we have something of this nature, it is not appropriate to just take it this way. Rather, what we do is write it linearly, that is, express it as a linear function. If we have to proceed with the method of undetermined coefficients, we should express this linearly first. So it is not being squared in this case. Okay, so it saves us from this headache of having to say, okay, what is this one? Can we simplify this further and all of that? Let us simplify it further before we do anything at all. So that is the process whenever we have this kind of expression. So we have learned from our mistake. Now let us correct that mistake. So we have seen that everything we've done from this point forward would not work. So let's isolate that as some rough work that authors some hard lesson. Okay, don't forget I said we're playing around with mathematics here to see some edge cases. So then what do we do from the beginning? We want to make this a some linear expression. So we now say that, but you should recall that cos, if you have cos 2x, you know that is cos x plus x. So that is, you know, from the formula for, let's say if you have cos a plus b, for instance, from trigonometry, that should be cos a cos b. So you can just revise trigonometry if you can remember this, minus sine a sine b. So basically, if you have cos 2x, that is cos x plus x, so you should be able to write that as cos x. That's going to be cos squared x, and then minus sine x, that is sine squared x. So basically, we can simplify this further. We know that cos squared x is 1 minus sine squared x. So we can write this as 1 minus sine squared x, then minus sine squared x, because cos x is 1 minus sine squared x. So by that, we can simplify this further. If we simplify this further, this is going to be equal to 1 minus sine squared x minus sine squared x. That's 1 minus 2 sine squared x. So what does this tell us then? This tells us that cos 2x equals 1 minus 2 sine squared x. So what did I write a again? Alright, so that means we can have sine squared x then as being equal to 1 make sine squared x the subject. That's going to be 1 minus cos 2x then divided by 2. So we can write it as 1 over 2 minus 1 over 2 cos 2x. So that saves us from trouble because this is now some linear term carrying a derivative. I mean a a trigonometric expression. So this is now cos ax. So it is still in the form to which we can apply our method of undetermined coefficients. So therefore, we can write f of x, which is given as sine squared x, as being equal to 1 over 2 minus 1 over 2 cos 2x. So with this, we are good to go. We have an expression for f of x. We clearly see that we can apply our method of undetermined coefficient to it. So we'll just go ahead and apply the method now. So to do that, we say that for this case, our f of x is equal to, so we'll identify the components we have here. This is some constant, so we can take that as 1. Of course, 1 and its all its derivative is just 1. And then we have cos 2x, that's another complement. So cos 2x will have its own UC set to be cos 2x, then and sine 2x, cos 2x, and sine 2x. So this captures everything we need. So the union of these two, so union of these two, that's 1 plus cos 2x, union of these two. Why are we just taking the union directly? Yeah, this is one term, this is one term. These are components that we did, but of course they also correspond to the terms present, so we don't need to do any other thing to get for the terms. And we can recall that the solution for our form of the equation is C1 plus C2x. This is C1 times 1 plus C2 times x. So do we have a 1 or do we have any term now in our UC sets for each of these terms that we have in f of x? Do we have any of them to carry 1? That's some constant. And do we have anyone to carry x? So let's go ahead and check that condition here. So you see this one is 1. So this is definitely linearly dependent on y1. Our y1 was 1. So that is linearly dependent on 1. So if y1 was 10, that is still linear dependence on y1. So that means that what we have here cannot be left alone. Okay, so we can't just take this union like that. So we have to modify this one because it is already part of our complementary function. Our y1 was obtained to be 1. Okay, this was c1 times 1 and c2 times x. So if we have x or 1 here, it can't work. So we have to modify this. So to modify that, we will have 1 to be, what do we do? Again, multiply through by x. If we multiply through by x, and we get x, we see that x is still present here, so that cannot work still. So we have to multiply by x again. That will give us x squared. So that is x squared, and that's when we are now free. So 1 should rather be represented by x squared. So at the end of the day, the union of the UC set for the terms present for 1 and cos 2x, don't be carried away by the fact that I'm writing 1 plus cos 2x. It doesn't matter. You might be wondering that this is going to be negative or this is going to be 1, but it doesn't matter. We're just interested in the terms. Okay. So this is going to give us the union of these two. Of course, we're taking the union of the verified ones. So we can see cos 2x and sin 2x are not present in the complementary function, so there's no problem with that. So the union will just be cos 2x, sin 2x, and x squared. So therefore, our form of the particular solution should be a cos 2x plus b sine 2x, then plus c multiplying x squared. So we will now go ahead and use this to evaluate. So this is going to be was when differentiated, this is going to be derivative of cos 2x, that's minus 2 sine 2x, so that's going to be minus 2a sine 2x. Derivative of sine 2x is 2 cos 2x, so this is going to be plus 2b cos 2x. And derivative of cx squared, that is 2cx. Alright. Then when we get our y p prime prime, so that's going to give us minus derivative of this. Derivative of sine 2x is cos 2x, so this is basically going to be minus, that's 2 cos 2x, so that's going to be minus 4a cos 2x. Derivative of cos 2x is minus 2 sine 2x, this is going to be minus 4b sine 2x. and then derivative of 2cx is 2c, so this is going to be 2c. So with that, we are good to go. We can now solve, we can now evaluate our, can now determine our undetermined coefficients. So don't forget that our given differential equation is y prime prime equals sine 2x. So, sorry, sine squared x. We are not putting sine squared x here. We are putting this simplified one. We have seen that sine squared x is equal to 1 over 2 minus 1 over 2 cos 2x. So this will be 1 over 2, 1 over 2 minus 1 over 2 cos 2x. That's what we're using here. This simplified one. We know that sine squared x is equal to this. Okay. So what is the next thing to do now? We will have this to be looking at y prime prime. So just identify all the terms present here. We have what is it here? We have cos 2x, we have sine 2x, we have the constant 1, we have x squared. So we have to take them one after the other and equate their corresponding coefficients. So I'm going with cos 2x first. What's the coefficient of cos 2x here? That is in y prime prime, that is minus 4a. So we're going to pick minus 4a. And that's all I have here, y prime prime multiplying 1. Then for this one, here cos 2x has coefficient of minus 1 over 2. So minus 4a should be equal to minus 1 over 2. That means 4a is equal to 1 over 2. It means a should be equal to 1 over 8. Then what is the next thing? This is going to give us sine 2x for the coefficients of sine 2x. In y prime prime, I have minus 4b, okay, to be the coefficient of sine 2x. So multiply by 1, that is still minus 4b, and that should be equal to, there is nothing here for sine 2x, that should be equal to 0. That means b equals 0. So the next thing is, what do I have? The constant. Okay, so, and the constant, that's the coefficient of 1 in everything. The coefficient of 1 here is 2c in my y prime prime, that is 2c. And the coefficient of 1 here is 1 over 2, so this is 1 over 2. So that means c equals 1 over 2 divided by 2, that is 1 over 4. What else do we have? We have x squared in these expressions. We also have what is it here? What do we call this now? X squared in this expression. That is um what do we call this now? If we consider this now, we have x squared. We can see that whatever it is that we have here, so this is going to be what is it now? Coefficient of um what do we have again? This is cos 2x, this is sine 2x, this is 1. So after that, what do we have? We have, what other term do we have in the expression? We have x and x squared. Yeah, we have x and x squared. So we know that this should be, we should have x right there, which is in our derivative. Okay, so if we pick x here, it doesn't have any, I mean, for y prime prime, it is not present at all. And for this side also, it is not present. So it's going to be 0 equals 0. So that is fine. If we consider x squared also, it is going to give us, for x squared, no x squared term is present here. So that's going to also give us 0 equals 0. So we don't really have any business with that. So it is not, there's no information now given to us about what the coefficient of, I mean, what's from what we have obtained here, we have obtained ABC. Okay, so what do we need in our given equation? We just need ABC. So you can see there is no information about or required or that should be obtained from the coefficients of x and the coefficient of x squared, because they are not present here. They are not present in the y prime, so they are not coming up in this equation at all. We already have all the coefficients that we need, so as expected. So if we have done the proper thing, we should have all the coefficients that we need already. So we are good to go. By that, we can now write out our final expression. So that means now that by this solution, our y particular will be equal to, so it was a cos 2x. So we found a to be 1 over 8. So this is going to be 1 over 8 cos 2x, then plus b sine 2x. So our b is 0, so just ignore that, 0 sine 2x. Then our c, will see x squared, so this will be plus 1 over 4 x squared. So this is plus 1 over 4 x squared. So with that, we have now found our particular solution. So you can play around with this. For instance, get its second derivative and convince yourself that it is going to give you 1 over 2 1 over 2 minus 1 over 2 cos 2x, which is just the same thing as sine squared x. So with that, we are good to go. For instance, just for rough work, to be sure that we've done the proper thing, if you differentiate this, this is going to give you minus 2 cos 2x, so that's minus 2 over 8 sine 2x, sorry, because the derivative of that will be sine 2x, and this will be plus 1 over 4, so this will be 2x over 4, that is going to be plus 2x over 4. And of course, if you differentiate this again, you're going to have the derivative of sine 2x is cos 2x, so this will be multiplying 2. This is going to be minus 4 over 8 cos 2x, and this will just be plus 2 over 4. So this is 1 over 2 minus 1 over 2 cos 2x, which is what we have seen was equivalent to sine squared x. So that is that about that. This is our y particular. We found it, we verified it. So we're good to go. So we've solved the equation now. We've solved the equation as expected. So we can now write out our final solution or our general solution. Y should be equal to y complementary plus y particular. So what is our y complementary? What's our y particular? So let's just get back up there. Our y complementary is c1 plus c2x. So we'll write that out here. So this is meant to be c1 plus c2x. What is our y particular? We just got that here. That's 1 over 8 cos 2x plus 1 over 4 x squared, and that gives us our result. So that is our solution to the given differential equation. It's actually very simple to find. You know, we were doing exploration. That's why it took us so long. It's very simple to find. When you have sine squared x or cos squared x, you know, cos squared x also can be simplified. We know that from what we did, then we saw that cos 2x was equal to cos squared x minus sine squared x. So we could also have written it as cos squared x minus sine squared x. Sine squared x will now be 1 minus cos squared x itself. So we would have this to be 2 cos squared x minus 1. So if we add cos squared x, we could make it a subject and still write it in terms of cos 2x. So that will give us a linear expression here, to which we can apply our method of undetermined coefficient as usual. So when you have this product here, you can still apply the method of undetermined coefficient, but in that case, please simplify it first to the linear term, as we have seen here that if we don't, it's going to result in some error because of the fact that a particular term will be dependent on some other term appearing elsewhere. So we want to avoid that linear dependency. We see that this is actually dependent on this, so that's why it was resulting in this issue or this problem we came across. So to avoid that, this is the best way to deal with this kind of problems. So that's that about this problem. So let's solve one more interesting problem, edge case. And I did mention this when we talked about first order ordinary differential equations, particularly when we dealt with applications of first order ordinary differential equations to electric circuits. We obtained an interesting equation then, which was a linear first order differential equation with constant coefficients. So we said that the concept we developed here, we developed them considering second order differential equations, but they can be applied to linear differential equations with constant coefficients, non-homogeneous, of any order. So we can apply this concept to still solve first order differential equations. In fact, it gives us a very simple way to solve some first order differential equation. That is just the best way to solve this kind of first order differential equations. So let's quickly examine that problem. Yeah, I'm reproducing the differential equation for what to obtain then. Let's move into that here. So we add them. So we can get back to that. Application to electric circuits on application of first order ordinary differential equation. Then we did obtain the charge with respect to time to be the q dt plus 4q equals 2 cos 2t. So if you recall, then we had to do a lot of integration. I mean, we had to integrate this. We had to get the integrating factor, then integrate mu q, which required us to find to use the product rule twice, which we saw that was extremely long. So here, there's actually a simpler way to deal with this. So this is a non-homogeneous first order linear ordinary differential equation with constant coefficients. And what we have on this side is a function to which we can apply our method of undetermined coefficient. So with that, we are good to go. So what do we do here? The same process. We say that in this case, we're given the q, the t, so plus 4q to be equal to 2 cos 2t, okay, and its homogeneous part. So let's identify the homogeneous part first. The homogeneous part is, what is its homogeneous part? That is the q dt, okay, plus 4q equals 0. And Root's auxiliary equation, so we identify that quickly. Whose auxiliary equation is, what's the auxiliary equation now? It does have q prime here, so this is m, so we just have that as m, then plus 4 multiplied by that's 4 equals 0. So from here we see that m is equal to minus 4. There's just one, there's just power of one, so we expect only one solution. So we can't say this is we're not comparing with any other to say maybe they have equal roots, real and distinct roots. This is just real roots, okay? So there's no other thing to check. So that means that in this case, our complementary solution is just going to be C, that's constant. There's only one constant, so there's no need to name it C1. Exponential minus 4C. Okay, sorry. Our dependent variable here is q, so let's write this as qc. So the complementary solution here will be qc will be c exponential minus 4t. Why? Because m is minus 4, it is distinct, so it's just going to be c. You know, if we add to it, to be c1 exponential, this one t, then plus c2 exponential, the other one t. So I just want, so there's nothing to add to it. There's nothing to compare it with to say whether it is equal to the other one or not. So this is going to be our complementary solution. And that is to tell you that now you could solve this. You know, this is a separable equation, so you could solve it as well the way it is here using the idea of separable equation that we have learned before. We talked about that when we talked about the homogeneous equations aspect too. So you could solve this as a separable equation, you will still obtain these results. Yes, you still obtain this, so you can check that for yourself if you don't believe me. So then we will consider our f of t. In this case, we call it f of t because t is the independent variable. So we now say that from f of t, what is f of t here? Our f of t is 2 cos 2t. So this is going to be 2 multiplying cos 2t. So we'll pick the terms present. So the only term here, sorry, they will pick the components present. The only component present here is cos 2t. So its UC set is going to be cos 2t and sine 2t. So that's quite easy. We ask ourselves, do we have any of these present in the complementary solution? No, we don't have anything here that's linearly dependent on this. We know this is for the components. It's also for this term. That's the only term present. There's nothing to take any. There's no other units. Union to take or anything because there's no other term present. So that means that y particular should take the form a cos 2t plus b sine 2t. So that is that about that. So we'll take its first derivative only. How am I calling this y? It's meant to be q, please. Q is the dependent variable here. So this should be q. I'm just kind of used to y. So I don't know why I'm used to y. So this is qp, and that is going to be derivative of this with respect to time. So qp prime is what we're interested in. Derivative of this with respect to t. Derivative of cos 2t, that is minus 2a sine 2t. Derivative of sine 2t, that will be 2 cos 2t, so this will be plus 2b cos 2t. So with that, we're good to go. We will now substitute into the given equation. So our given equation is q prime plus 4q equals 0, or q dots if you like. So this is q prime plus 4q equals not 0, please. This is the homogeneous part. We are using the given equation directly. Is equal to 2 cos 2t. So this is 2 cos 2t, 2 cos 2t. All right, so by that, we know that we only have sine 2t and cos 2t present in the whole thing. So let's just pick their coefficients directly. So coefficient of cos 2t, what's the coefficient of cos 2t in q prime? Cos 2t has coefficient of 2b, so we'll take note of that. That is 2b times 1, that's 2b. Then in q, uh, cos 2t has coefficient of a, then multiply by 4, so that will be 2b plus 4a, and that should be equal to coefficient of cos 2t here, that is 2. When we divide through by 2, we will have b plus 2, sorry, yeah, b plus 2a, okay, equals 1. So let's keep that as equation 1 because we have two unknowns, we can't solve them yet. So then the next one is to consider sine 2t. So for sine 2t, the coefficient in q prime is minus 2a. So take note of that, minus 2a, because times 1 is minus 2a. Then in q, coefficient of sine 2t is b. So that will be b multiplied by 4, that is plus 4b, is equal to the coefficient of sine 2t here is 0 because it's not present. So this will give us, dividing through by 2, this is going to give us minus a plus 2b equals 0. So this implies that, this second equation implies that a equals 2b. So if a is 2b, then we can replace a by 2b here. So in this case, we're going to have b plus 2 times 2b as b plus 4b, that is 5b. So is equal to 1. So from that, we get b should be equal to 1 over 5. And since a is equal to 2b, then a will be equal to 2 over 5, basically. So by that, therefore, our particular solution, q particular, will be 1 over 5, okay, 1 over 5, where is it again? 1 over 5 cos 2t. A is 2 over 5, sorry, so this will be 2 over 5 cos 2t, and then our b is 1 over 5, that's plus 1 over 5 sine 2t. So this is plus 1 over 5 sine 2t. Alright, so that's our particular solution. And from this, we can get our final solution. So thus, the final solution or the general solution, q as a function of time now will be q complementary plus q particular. So therefore, q as a function of time will be equal to q complementary. What was that? c exponential minus 4t. So this is going to be c exponential minus 4t, then plus the q particular, that is plus 2 over 5 cos 2t plus 1 over 5 sine 2t, and that is the final solution. So you can go back to check that this was the solution we obtained in that lesson under applications of first order ordinary differential equations, and we obtained it after we went through a lot. We actually literally went through a lot to get the integral by using what's it now, product rule of integration twice before we were able to get that integral. But this method does not involve any integration, so it's quite simple, like very simple to deal with. So you can see the process is just very straightforward. No integration required. The only thing we did was differentiation. So that is the usefulness, the advantage of this method of undetermined coefficient. That is the end of this lesson. In the next lesson, we'll begin to talk about the method of variation of parameters to see how it works, and we'll consider some examples on it as well. Thank you for watching. We'll see you in the next lesson.